Our team prepared Chapter 7. The title of Chapter 7 is Quality Assessment. The last presentation is Chapter 6. The title of Chapter 6 is Creation and Enrichment. Next is the introduction of our team. There are 3 members and we each took charge of the parts and produced the presentation. First, Dong-Jong will explain the introduction and 7.1. Second, Ye-Eun-shin will explain the part 7.2 and 7.3. And last, Hoon Park will explain the part 7.4 and 7.5. This is our outline. First section is accuracy, second section is coverage, third section is coherence, fourth section is succinctness, and last section is other quality dimensions. Independent of the source from which your node knowledge graph is created, initial node knowledge graph will usually be incomplete, will often contain duplicate, contradictory, or even incorrect statements, especially when taken from multiple sources. After the initial creation and enrichment of a node knowledge graph from external source, a crucial step is thus to assess the quality of the result node knowledge graph. Quality assessment then helps to ascertain for which purpose a node knowledge graph can be reliably used. For example, take the sample of an initial node knowledge graph created by the theorist board shown in this figure. Let me ask you a question. Is this node knowledge graph of good quality? Does it exhibit issues that might limit the application for which it is fit for purpose? Can we define and detect such issues? I'll give you the answer first. This answer is challenging to address in a general way. This chapter discusses sometimes overlapping quality dimensions. This chapter that capture qualitative aspects of the multifaceted notion of data quality. Some of these dimensions are more general to database, while others are more specific to node knowledge graphs. We further discuss quality metrics that provide ways to measure quantitative aspects of these dimensions. We group dimensions and metrics in a manner inspired by Battini and Scarnapieco. Occurrence refers to the extent to which entities and relations encoded by nodes and edges in the graph correctly represent real-life phenomena. Occurrence can be divided in 3 dimensions. First, syntactic accuracy, second, semantic accuracy, and last, timeliness. Syntactic accuracy is the degree to which the data are accurate with respect to the grammatical rules defined for the domain and or data model. A prevalent example of syntactic inaccuracy occurs with data type nodes, which may be incompatible with the defined range or be malformed. For example, assuming that a property start is defined with the range date time, the value March 22, 29 in figure would be incompatible with the defined range, while the value March 22, 29 datetime would be malformed. A corresponding matrix for synthetic accuracy is the ratio between the number of invalid values of a given property and the total number of values for the same property. Such forms of synthetic accuracy can typically be assessed using variety tools. Semantic accuracy is the degree to which data values correctly represent real-world phenomena, which may be affected by imprecise extraction results, untrustworthy source vandalism, etc. For instance, in figure, the start of the 15th event comes after the end of the event, possibly due to a typo in the year. While such a case could potentially be identified using, for example, shape-based validation, other cases might be more difficult to detect. For example, if we were to accidentally and incorrectly swap the values for Edge 15 and Edge 17, there might be no indication whatsoever in the node knowledge graph that the values are incorrect, even if we have additional scimitar ontology rules available. Assessing the level of semantic inaccuracy is challenging. While one option is to apply manual verification, an automatic option may be to check the start relation against several sources. An alternative is to validate the quality of the process used to generate the node graph based on measures such as precision, possibly with the help of human experts or gold standard. Timeliness is the degree to which the node graph is kept up to date with the real-world state. A node graph may be semantically accurate now, but may quickly become inaccurate if no procedures are in place to keep it up to date in a timely manner. Considering this figure, the events appear to be from years ago, and if not updated, then the node graph will not be suitable for application that wish to recommend it upcoming events to user. Additionally, the meaning of some values in the graph, such as next Tuesday or next Thursday, will change over time and become semantical inaccurate in the future. Similarly, the age of Santiago will quickly become outdated, where instead representing the year that the city was founded would postulate timeliness. Timeliness can be assessed based on how frequently the node graph is updated with respect to underlying source, which can be done using temporal annotations of changes in the node graph, as well as contextual representation that capture the temporal variability of data.
Next, I will talk about the completeness and representativeness of coverage and consistency and validity of coherency. Coverage means that avoiding the omission of the main relevant elements which otherwise may yield incomplete query results or entailment bias models, etc. Next, completeness means that the degree to which our required information is present in a particular dataset. Completeness comprises the following four aspects: schema, property, population, linkability. First, schema completeness refers to the degree to which the classes and properties of a schema are represented in the data graph. Next, property completeness refers to the ratio of missing values for a specific property. Third one, population completeness refers to the percentage of all real-world entities of a particular type that are represented in the datasets. Last, linkability completeness refers to the degree to which instances in the dataset are interlinked. For examples from this figure, the lack of information about the fare for EID 15 might be seen as a form of property incompleteness, while missing events held in Chile around the same time might lead to population incompleteness. Measuring completeness is non-trivial as it assumes knowledge of a hypothetical ideal knowledge graph that contains all the elements that the knowledge graph in question should have. Concrete strategies may involve comparison with gold standards that provide samples of the ideal knowledge graph, or measuring the recall of extraction methods from complete sources. Representativeness is a related dimension that focuses on assessing high-level biases in what is included, excluded from the knowledge graph. And dimension assumes that the knowledge graph is incomplete and asks how biased this sample is. Biases may occur in the data or in the schema or during reasoning. There are three examples of data biases. First, geographic biases that underrepresent entities, relations from certain parts of the world. Second, linguistic biases that underrepresent multilingual resources, for examples, labels and descriptions for certain languages. Last, the third one, social biases that underrepresent people of particular genders or races and so forth. Unrecognized biases may lead to adverse effects. For example, if the knowledge graph of this figure has a geographic bias towards events and attractions close to Santiago City, then this may lead to tourism in and around Santiago being disproportionately promoted to the detriment of tourism elsewhere in Chile. Next, coherency refers to how well the knowledge graph conforms to the formal semantics and constraints defined at the schema level. Consistency means that a knowledge graph is free of contradictions with respect to the particular logical entailment considered. For example, if we apply the entailments defined in Table 4.1 over the graph of right figure, we see that the edge Santiago de Chile, same as Santiago de Cuba, is inferred from both entities being the same as Santiago, which generates an inconsistency with the edge Santiago de Chile different from Santiago de Cuba as stated in the graph. While in this case, considering the venues connected to Santiago are in Chile, it is evident that Santiago de Cuba, same as Santiago, is semantically inaccurate. In other cases, there may not be an obvious inaccuracy. Take for example the ontology defined in figure 7.2 combined with the graph of figure 7.1. According to ontology, the food festival EID 15 offers takeaway service. This entails that EID 15 is a restaurant, a building, and a place which is disjoint with event. However, EID 15 is also entailed to be a festival and then an event which creates generating an inconsistency. And in this case, there is no clear individual arrow leading to an inconsistency. Validity means that the knowledge graph is free of constraints violations, such as captured by shape expressions. For example, specify a shape city whose target nodes have at most one country. Then, taking the edges from figure 7.1 and assuming that Santiago becomes a target of city, we have a constraint violation. Conversely, even if we define analogous cardinality restrictions in an ontology, this would not necessarily cause an inconsistency since, without UNA, we would first infer that Chile and Cuba refer to the same entity. Similarly, using shapes, we can more easily detect missing data. For example, we can define a shape event and require that it have at least one value for the property pair. Now, if EID 15 becomes targeted by event, then we will have a constraint violation as the node has no value for pair. Conversely, even if we define analogous cardinality restrictions in an ontology, this would not cause an inconsistency since under the OWA we would rather entail that the event EID 15 has some pair.
Chapter 7.4 describes succinctness. Succinctness refers to the inclusion only of relevant content, that is, represented in a concise and intelligible manner. Succinctness is important to effectively manage the knowledge of the data. In this session, I will talk about conciseness, representational conciseness, and understandability. Conciseness refers to avoiding schema data elements that are irrelevant to the domain. Mendes et al. Distinguish intentional conciseness, which refers to the case when the data do not contain redundant schema elements, and extensional conciseness, where the data do not describe redundant entities, and relations. This is for example, the inclusion of a property and class for modeling jurisdictions and legal entities. In the ontology of figure 7.2 may affect the intentional conciseness of the ontology in the context of a knowledge graph about tourist events. Similarly, the inclusion of data about Santiago de Cuba in our knowledge graph dedicated to tourism in Chile may affect the extensional conciseness of the knowledge graph, potentially returning relevant results for the given domain. In general, conciseness can be measured in terms of the ratio of properties, classes, shapes, entities, relations of relevance to the domain, which may in turn require a gold standard or measures of domain relevance. Representational conciseness refers to the extent to which content is compactly represented in the knowledge graph, which may again be intentional or extensional. This is, for example, having two properties, category and type, serving the same purpose, would negatively affect the intentional form of representational conciseness. While having two nodes, Santiago and Santiago de Chile, that split the data available about the capital of Chile, would affect the extensional form of representational conciseness. Another example of poor representational conciseness is the unnecessary use of complex modeling concepts, such as using reification unnecessarily or using linked lists when the order of elements is not important. An example of this is the anonymous node used in figure 7.1 to represent the dates on which EID17 starts and ends, which could neither be directly associated with the event. A different example is the specification of the duration of EID15, which could be calculated from the start and end values. Third, representational conciseness is challenging to assess. Measures such as the number of redundant can be used. Next content is understandability. Understandability refers to the ease with which data can be interpreted without ambiguity by human users, which involves and lists the provision of human reliable labels and descriptions that allow such things. Measures of understandability may include the ratio of nodes with human relevant labels and descriptions, the uniqueness of such labels and descriptions, the languages supported, the list of quality dimensions provided here should be considered illustrative rather than complete. For more discussion, we refer to the survey by Taveri and to the book by Patini and Skenapico. Thank you for our presentation.